Okay, we're very happy to welcome everyone back to the MOPA seminar for the fall 24 semester. We have all several talks lined up for going through December, so keep an eye out for the emails on those. And so first we have Sun Mengzhou from National University of Singapore speaking on the Kaufmann-Clote question on end extensions of models of arithmetic and the weak regularity principle. Go ahead.
Yes, thank you for the introduction and also thank you for the opportunity of speaking here. Right. Is there any echo? Uh, okay. Anyway, so I'm going to talk about the connection between an extension of models of arithmetic and certain kind of regularity principle. Okay, and here is my general setup. Okay, I will the general background for fragments of first and second order arithmetic. We have a language of first order and second order arithmetic, and we can define the delta zero, sigma n, and pi n formula in a Euro way by counting the number of unbounded quantifiers. And we can define a formula as delta n if it is equivalent to both a sigma n and pi n formula. And over some model theory, we have two class of axioms: the induction for sigma n formulas and the collection for sigma n formulas. So collection means if you have for any x less than a, there's a y, then you should have an upper bound b for all the width is y. And the relation is I sigma n implies b sigma n, and also b sigma n implies I sigma n minus 1. And by Paris-Kirby, none of the converse holds. And all these are the same if we go to second order arithmetic. You just put superscript 0 here. And we need to make use of a bit more second order arithmetic, but it's just from some definition. So RCA0 is I sigma 1 plus delta 1 comprehension, and WKL0 is RCA0 plus a statement saying that every infinite binary tree has an infinite path. Okay, so this is all the notation we need. We want to study the extensions of models of arithmetic, and in particular, we want to look at certain kind of extension called n extension. So we say that K is an n extension of M if for any new element X, and it should be greater than all the old element Y. So the typical example should be like, okay, so this is K, and this is M. So basically, M is the initial segment of K. And we say that it's proper if they are not the same, and it is an elementary if all the sigma n formula is absolute. Okay. And okay, so this is the most classical theorem in this topic, the McDonald-Specker theorem. It says that every modulus of PA has a fully elementary proper n extension. And later on, Paris and Kirby, they have a hierarchical version of this McDonald theorem, of this McDonald-Specker theorem for fragments of PA. And actually, they show that actually this kind of n extension with elementarity can characterize the strings of collection in a ground model. So actually, they show an equivalence, namely, if you can n extend to some k properly with n plus 2 elementarity, this is equivalent to say that you have a sigma n plus 2 collection. And in particular, the converse of the McDonald-Specker theorem holds. And the direction from right to left, we do not need the countability. And from the left to right, we don't need countability. And from right to left, we need countability. Okay. And this Paris-Kirby theorem is like the prototype of today's talk. I'm going to I'm going to try to generalize this theorem in different ways. Okay, so here is some motivating question. So the first one is the equivalence is the characterization of collection, right? And we want to have another version of an extension property which can characterize the induction in the ground model. Okay, so this is the first question. And the second question is, in this equivalence, on the left-hand side, there's no restriction on on what kind of theory T this K may satisfy. And we can trivially have K satisfy I sigma n only by the elementarity. And Paris and Kirby, they show that we cannot always have K satisfy I sigma plus 1 because that will imply M satisfies the next level of collection. Okay, so in the IB hierarchy, the only question is, can we have this K to satisfy B sigma plus 1? And that is the question of Kaufmann and Clote. Okay, so this question is due to Clote, and he mentioned that the same question is raised by Kaufmann in the context of models of set theory. But I have no idea of that question. And this is essentially the question. So does every countable model of B sigma n plus 2 has a proper n plus 2 elementary n extension K, which satisfies B sigma n plus 1? Okay, so, and I'm going to answer this question positively. So the answer is yes. But on the other hand, okay, go back to this question. By setting this K to satisfy B sigma plus 1, we do not get some more information about the ground model. And in the end, I will show that another n extension property will characterize M satisfies I sigma plus 1. And that is another theory T this K satisfies. So I will temporarily tell you another story, the regularity principle. And in the next slide, I will show you how these two are related. Okay, so this is the definition of regularity principle. It's defined by this formula. And you can view this phi as a way of coloring. This X is the element and Y is the color. So our assumption says there are cofinally many element X, which is colored by some Y less than A. And our conclusion says there is a color Y less than A, such that there are cofinally many X's colored by such Y. And this is introduced by Mills and Paris, and they show that actually regularity principle is equivalent to collection. And we are going to show in the next page that if we have certain kind of n extension with elementarity, then in the ground model, it satisfies certain kind of regularity principle. Okay. So this is done by a non-standard analysis argument. We can view the n extension as certain kind of like hyper extensions, and the elementarity is like the transfer principle. Okay, so this is an example, and this is exactly one of the direction in Paris-Kirby theorem. If we have such an n extension with elementarity, then M satisfies R pi n, and this one is equivalent to B sigma plus 2. So this is one direction. And here we give a simple proof here. Okay, so the idea is we want to like, is there any questions? Okay. So if you have any question, please stop me. So the idea is we want to like apply the color to K. And that means we want to transfer this fact to K. In M, we know that there are cofinally many X's colored by some Y. And this statement is a pi n plus 2 statement, so that our elementarity will transfer this statement to K. And K also knows that there are cofinally many X is colored by some Y. so that we can pick a D which is greater than M in K, and it is colored by some C. Then for any B in M, K models there exists X greater than B, which is colored by C, and this is witnessed by D. And this one is also a sigma n plus 1 statement without any parameter in K. So we can go back to M using the elementarity again. And then after you transfer each of these statements back to M, then actually you get their cofinally many element in X, which is colored by C. So that is a proof. And in the following, I will try to generalize this argument by setting some requirement on K, so that it's like if we have more induction or collection in K, then we can transfer more and more complex coloring to K and then go back to M. Okay, so here is an immediate example. If we have such a extension in the Kaufmann-Clote question, this one
Can I
is
see
yeah.
the definition of the regularity principle again?
Yep. Okay, so maybe I need to copy
Just
the definition to
just
the next page.
just leave it up for a second so I can kind of think about it.
Can I say something? Is the regularity principle just, formulated in models of arithmetic for the pigeonhole principle?
You can build this as an infinitary pigeonhole principle. I can say
Right.
yes, yes.
Okay, so that's what it is. Okay. That's
Yeah.
what yeah.
Yeah. Thank you.
Okay, so I continue.
Yeah.
Okay. Okay, and next is another example. So this one is exactly what we want in the Kaufmann-Clote question, right? If we have such an n extension K, which satisfies B sigma plus 1, then we claim that in the ground model we have the following version of regularity. So this one is very similar to the regularity principle, but there are two differences. One is here phi is pi n plus 1, not pi n. Phi becomes complicated. But instead of saying that there are cofinally many x, we say that for any x is colored by some y. Okay, we want to use the same argument to show this. And the proof is actually essentially the same. So in M, if we satisfy this, we want to transfer this statement into K. And this formula is pi n plus 1, is pi n plus 2, but the equivalence only holds over B sigma plus 1. And now since M and K, they both satisfy B sigma plus 1, so that this statement will correctly transfer to K. And then in K, we know that for any x in K, it is colored by some y. So we can pick an element which is greater than M, then all the argument just goes through. So it's the same proof, but when the coloring applied to K, we need to make use of the assumption that K satisfies B sigma plus 1. Okay, so this is the same proof. And we call this the weak regularity principle. So we call this weak because we replace the assumption of their cofinally many by for any. And the immediate glory is that if the Kaufmann-Clote question has a positive answer, then for any countable models of B sigma 2, we can first n extend it to K, which satisfies B sigma plus 1, and we run this argument to prove the weak regularity, right? So that we have this implication. And before I go into the construction of the Kaufmann-Clote question, I first want to say something about the syntactic proof of this one. And the idea in the proof will inspire the construction. So here is a syntactic proof. The proof is a bit, it's very easy, but it's a bit interesting because our proof actually go to the second order, actually go to the second order arithmetic, and we need to make use of WKL0. We need to use the weight conic lemma. Okay, so here's a statement. B sigma 02 plus WKL0 implies the weak regularity for pi1 formula. And the idea is, so suppose we have for any x, it is colored by some y, and the coloring is a pi1. Then we can construct a branching tree defined like this, right? Sigma in T, if and only if for any xz less than the length of sigma theta x sigma xz. So this definition, the idea of this definition is like we try it's like for each x, this sigma x is an approximation of the correct coloring y, right? We try to approximate the correct coloring. I say this is approximation because in the definition this is a universal quantifier, right? And we replace it by a bounded universal quantifier bounded by the length of sigma. So it might not be the true color y we want. It is just approximation. But if we have an infinite path, then the length of sigma go to infinity. Then this bounded quantifier becomes an unbounded quantifier. And along that path, all the sigma x will be the correct color y. So that's where we need to use WKL0. And with the help of I sigma 1, actually we can show that this tree is infinite because for each length L, we can find the correct choice of sigma by some coding ability. And then we apply WKL0 to find an infinite path P of this T. And as I just said, this path P will correctly choose the color. And because we're working in a second order context, we still have B sigma 2 relativized to P, right? And that means we can pick a color C less than A such that they are cofinally many x, P of x is equal to C. And here we apply B sigma 2. So this is the proof of the second order version. And the original first order version here is just done by some relativization argument. You go to the case of B sigma 2, and we expand the model of B sigma 2 to a model of WKL0. Okay, so this is a syntactical proof. And the question is, how does this argument relate to our construction? Okay, so here are some clues. So the Paris-Kirby's construction is actually a first order delta m plus 1 ultra power construction. And that means it is an ultra power where all the objects are delta m plus 1 definable. They work on the Boolean algebra of all the delta m plus 1 definable subsets, and they work on all the total functions which are delta m plus 1 definable. Okay, but actually one can show that such first order ultra power will always fail to satisfy B sigma plus 1 in the Kaufmann-Clote question. And also the proof above indicates that we need to use WKL0 somewhere. So we need to work with a second order context. So all the clues indicate that we need to do some ultra power in the second order arithmetic. Okay, and here is our definition of ultra power in the second order arithmetic. I think this is due to Kirby, and this is basically the canonical way of doing ultra powering in a second order context. We have an ultra filter U on the second order universe curly X, and we require that all the elements in U are cofinal in M. And ultra power should be the class of total functions in X and module some relation given by the U. So it is pretty standard But one thing is different. We need, in our case, we need to equip a second order structure on the ultra power, and it is directly inherited from the second order structure in the ground model. So for any A in this curly X, we define F in A if and only if the corresponding set is in ultra power. And we also have the Woosh theorem, which is done by Kirby. We have the Woosh theorem for sigma 0, 1 formula. So the ultra power satisfies something pi 1. The ultra power satisfies something sigma 1 if and only if we can pick an element in the second order universe such that the corresponding sigma 1 definable set in the ground model contains this set and is in U. And in particular, this set is cofinal. And also we can show that we have the amount of elementarity we need. And here is the second order, and here the elementarity is second order since we have some second order parameters. Okay, and here is the construction. So again, by the relativization argument expansion to WKL0, we can reduce to the case of B sigma 02 plus WKL0. And we want to construct the ultra power, which satisfies B sigma 1, and it's an N extension. Okay, so there are two requirements. So the argument for the N extension is actually very standard, and it is exactly the same as the original Paris-Kirby's proof. So it's like for each of the elements F in ultra power, if F less than A is forced to be true, then by Woosh theorem, that means we have this set is in ultra filter. And in particular, this set is cofinal. So by B sigma 2, we can pick a B such that Fx is equal to B. This set is also cofinal. Then we just throw this set into the ultra filter. And by Woosh theorem again, it will imply that F is equal to B in ultra power. And otherwise, we can just force the negation of this statement. We just throw the opposite of the set above into the ultra filter, and we'll have F is greater than. So this part is pretty standard. And for the other part, you need to make use of
Mengzhou, can I just ask a small question? What
Yes.
do you mean by that the statement is forced?
Okay, so you
Forced
can
to be true.
okay, you can view the okay, so it's
So
is
it's
not
part of
strict.
the construction then that either you
Yeah,
have
yeah.
to do it. Okay.
Yeah, it's not a very strict definition. It's like you view the ultra power construction as certain kind of forcing. And by saying that this is forced, exactly, I mean, okay, so you enumerate all the elements in the ultra power. No, you have okay, so a construction consists of omega many steps, and each step you throw some element into the ultra filter. And I say that this is forced. I mean, at some stage, I already say that this set is already thrown into the ultra filter. And
I see.
by Woosh theorem, this means this one is already true.
All right, thank you.
And okay, so this is the next part, the part of B sigma 1. So we still do it in a step-by-step way. We try to force all the instances of B sigma 0, 1 to be true. And the typical instance of B sigma 1 look like this. Okay. And and here G is upper bound and F is just a parameter. The strategy is very naive. It's like we always try to force a conclusion to be true. And if we can do this one is a sigma 1 statement, right? If we can do this, then by Woosh theorem, it means we try to set the corresponding sigma 1 set to be in ultra filter. But in this case, I mean, I pick a subset of it in the second order universe and throw it into a lecture filter. If we can do this, then we're done. We just force the conclusion to be true. And if we cannot do this, that is because this set is bounded. Then we can use this information to argue that our assumption is already false. Okay, so here is the argument. So the failure just means this set is bounded. And applying B sigma 1, this is equivalent to say that for any x greater than b, there is a y less than g of x for any z negation of theta. And this one looks very similar to the assumption of the weak regularity principle, right? Except there is a greater than b part, but you can ignore this. And also in the assumption of weak regularity, the g of x should be replaced by the fixed upper bound a, but this does not matter in our proof. Okay. And similar to the previous argument, we can construct a finite branching tree. So this time it's not an A branching tree for some fixed A. Instead, it is a finite branching tree where the number of branching is bounded by G. And still we can, and also WKL0 also apply to this tree. And we can find an infinite path of this tree. An infinite path means a total function P, which is bounded by G. And along this path, P of x is exactly the correct witness of this Y. So we have this. And this one essentially will provide a witness of the failure of our assumption. The equivalent class of P will provide a witness of the failure of assumption of B sigma 1, so that in the previous slide, we force the assumption to be false. So in either case, we let B sigma 1 to be true. Okay.
Could I ask a question?
Yes.
I don't see, so the weak Kernig's lemma version that you're looking at in second order arithmetic allows parameters from the second order part because it's not obvious. You know, otherwise you have a finite tree, so finite branching tree where at the nth level it's bounded by g of n, but g is maybe an increasing function.
Yes, of course.
So the argument hinges on the fact that you're using this parameter g, which belongs to the second order part.
Yes.
So that's hence my question. And I don't see how it's obvious that if you have weak Kernig's lemma holding in the first order part, how it can be extended to hold in the second order part. Because you have the parameter g from the second order part that appears in your application of weak Kernig's lemma.
Okay, so I mean, how do you explain this? I mean, I omit one part is actually weak conic lemma is equivalent to the following one. I write it down, sorry. Okay, so what I use is here. Okay, so it's WKL0 is equivalent to every bounded,
right?
Every bounded, no, every finite branching tree, finite, no, not bounded. It's just finite. Where is my pointer?
Oh,
Every finite.
My ignorance, yeah. So there's no uniform bound. That's not required by weak Kernig's lemma.
Branching tree T, where the bound. Sorry for my writing. Where the bound is bounded by some G in the second order universe.
Okay.
If T is infinite, then it has a path. Weak-conic lemma can prove this.
Okay. Thank you. Sorry for the question. Yeah.
Yeah, I cannot.
No, I see, but just to clarify even further, Tom, when G is part of the second order structure, for any second order structure, or there's some assumptions needed on this X as well?
Can I say something, Roman? I'm sorry for the coarseness of my voice. This is a standard fact, namely,
Yeah.
over RC0, weak Koenig's lemma is equivalent to what is known as bounded Koenig's lemma, which
Right.
says for any tree that's finitely branching and there is a function witnessing the finite branchingness.
Right, but where is this function?
Well, in the second order universe. So your second order universe.
So this is a second order axiom then.
Yeah, sure.
Right.
I mean, weak Koenig's lemma is a second order axiom. And it's about, so this structure, M script X is a two-sorted structure, right?
Right. So this is weak Koenig's lemma in MX. No, that's right. Sure.
Yeah.
Thank you. I was blindness on my part. Right. No, thanks.
Okay, so actually G is a function in the second order universe, and the branching of T is bounded by G. So we can apply the equivalent version of weak-conic lemma just as Clote just said. So I continue.
Yes, continue.
Okay, so, and we can find an infinite paths. And, okay, where am I? We can find this infinite, okay, so, yeah, I just finished the proof. Yeah, and we have the first order version of this. Okay, so the first order version is essentially the positive answer to the Kaufmann-Clote question. And let me check the time.
You got plenty of time. It's at least 25 more minutes.
Okay. Okay, so that is basically the end of the first story, the positive answer for Kaufmann-Clote question. And next we continue to analyze the strengths of the weak regularity principle. So we can show that the collection is equivalent to the wide range of weak regularity principle. So the strongest version equivalent to B sigma plus 2 is the weak regularity principles for sigma plus 1 or pi n plus 1 formula. So this one means it is a disjunction of a sigma plus 1 and pi n plus 1 formula. And the weakest version is the weak regularity principle for sigma 0, sigma n formula. So this one means the closure of sigma n formulas under Boolean operation and bounded quantifiers. Okay, and if we replace this disjunction by conjunction, then it will no longer be equivalent. We can show that this one implies I sigma plus 2. Okay, so that is pretty much we can get from the syntactical proof. And here is one more question. So for what formula class the weak regularity gamma is equivalent to I sigma plus 2? And in particular, does the converse of this implication holds? Okay, I'm going to show that this is indeed the case. I'm going to show that actually we have this equivalence. This equivalence is true. And the argument is a bit different. The argument will be a modal theoretic proof. And actually, it's turned out to be related to the first question I asked at the beginning of this talk, which is which n extension property can characterize M satisfy I sigma plus 2. Okay, so to do this, we need to introduce some other arithmetic axiom for the n extension. Okay, so this is we need to define the induction up to initial segment. So this axiom is specially designed for n extension. We assume that m is k is an n extension of m, and there are two equivalent definitions. So the first one is essentially the so-called strong collection. So this one is strong collection. It should be S sigma n plus 1. But it's not the full version of strong collection. We know that strong collection is equivalent to induction, but it's not the full version, because here we require that the upper bound A is always inside M, but we allow parameter in K to be inside this phi. Okay, so strong collection basically says for there's a B such that for any x has an A, if there is a Y, then there should be a Y less than the upper bound B. Okay, so this is the first one, and we can show that it is equivalent to some coding ability. So the second one says we can code arbitrary sigma plus 1 formula in K, also with some parameter in K, but up to some upper bound A in M. Okay, so the upper bound should be in M, but we allow parameter in K, and all these are K satisfies something, and we call it K satisfies Mi sigma plus 1. Okay. And we can show that we also have the corresponding non-standard analysis argument for this kind of principle. So if M extend to K with n plus 2 elementarity and K satisfies this Mi sigma plus 1, then M satisfies the weak regularity for sigma plus 1 and pi plus 1 formula. Okay, so the proof is is still the same. So this time, the coloring is like this form, and the bounding quantifier before the conjunction of a sigma plus 1 and a pi plus 1 formula is equivalent to a delta n plus 1 formula over I sigma plus 1. So that overall this one should be equivalent to a pi n plus 2 formula over I sigma plus 1. And if we do the equivalence in K, and since the upper bound A is in M, so actually we only need Mi sigma plus 1 for the equivalence in K. So again, this statement will correctly transfer to K, and the rest are the same. We pick a color which we pick an element which is greater than M, and then we look at its color. Okay, so this is the other argument for the connection between n extension and regularity principle. And here's a remark. So actually, the argument can show some slightly wider class of formulas. So namely, we can replace phi by we can allow phi to be a sigma 0 sigma plus 1 formula. But here we require that x does not appear in the bound of a bounding quantifier. And in particular, this argument works for phi, which is a Boolean operation of Boolean combination of sigma n plus 1 formulas. Okay, so this is one direction. From the n extension, we have some regularity principle in the ground model. And next, we want to do the construction. We want to show that M satisfies sigma n plus 2 induction suffice to do the construction. Okay, so this is the proposition we want to show. And again, we can go to the second order universe and do the second order ultra power. And this time we don't need the WK0. So in principle, we can do it in a first order sense. And before I say the proof, I want to mention that actually the proof is a generalization of one of the theorem in Clote. And it proves that if we have I sigma plus 2 in M, then we can always properly n extend to some k, which satisfies MB sigma 1 plus 1. And this one, the definition is exactly the same as MI sigma 1. No, MI sigma n plus 1. And here is the idea of the proof. The idea is like we, for each of the uniform sequence of sigma 1 definable sets AI, we try to put AI in the ultrafilter as long as we can. No, here by put the sigma 1 set into the ultrafilter, I mean put a subset of it into the ultrafilter. Right, because this one is not inside the ultrafilter. We can only put a subset of it into the ultrafilter. So it's like we are forcing sigma 1 facts as long as it can happen. Okay. And in practice, we also do it in a step-by-step construction. And at each step, we have some set which is already enumerated into the ultrafilter. Let's call their intersection, call it B. And the intersection should be cofinal. Then we take the largest code C such that all their intersection for AI, for I in C, and also intersect B, this set is cofinal in M. And by I sigma 2, we can have a largest code C. And then we put a subset of this set in the second order universe into the ultrafilter. And then such C will code the corresponding sigma 1 formula. So it's like, okay, so it's like if at this stage I is already in C, and that means we already force AI to be true in the ultra power, and we're done. And if I is not in C, and because of the maximalities, then in the future you cannot enumerate AI into the ultrafilter anymore, right? So that in the ultrafilter so that in ultra power we always have the negation of phi for I is not in C. So that such C will correctly code this sigma 1 set. So that is the idea of the proof. So if you look at the definition, okay, so actually we are trying to let K to satisfy the second definition of this equivalence. And if you look at the second definition, you can see that if we already have M and want to construct K to satisfy this property, then the interesting thing is actually the code is actually in M, right? So actually we are not finding the code. We are actually to build up the model okay, so we first decide the code, what is the code, and then we build up the ultra power, the N extension according to this code. So it's like we let the model to fit in that code. So it's kind of interesting. Okay, so this is the idea of the proof. And we have our characterization of I sigma plus 2 in terms of N extension. So M can be N extended to some K with N plus 2 elementarity, where K satisfies M I sigma plus 1. This is equivalent to M satisfies I sigma plus 2 for countable models. And another consequence is we have implication from I sigma plus 2 to this weak regularity principle for this for the conjunction. For each of the countable model of I sigma n plus 2, we can first have an N extension satisfying this property, and then we run the previous proof so that the ground model will satisfy this weak regularity principle. And this time we do not have a syntactical proof. The proof is model theoretic, and I want to ask that is there any syntactical proof? But I don't know for now. Okay, I think that's all for my talk. And here's a summary, and thank you for listening.
Okay, great. Let's thank our
Yes.
speaker. Looking for my little emoji hands. And go ahead, Peter, you have a question?
Yes. So this may be an entirely dumb question, so please excuse any dumbness. Um, weak Koenig's lemma, as I recall, concerns binary trees.
Yes.
So that's not the case here. You've got the branching bounded by a function from the second order.
Yeah. Yes, but it's
So
provable from WKL0.
that property is provable from the binary tree representation version of WKL0.
Yes.
Okay, because
Uh,
it's not obvious to me. I mean, you're going from a binary tree essentially to a finite branching tree where the branchedness depends on a second order parameter.
yes. The point is the point is the branching is controlled by a function which is in the second order universe.
Right, right.
And
So,
okay.
are you giving the sketch proof of going from binary to being branching bounded by a second order parameter?
I think this
So,
is a standard proof in I think maybe in Simpson's book. I think.
Oh, okay. Sorry. It's just ignorance on.
Leszek, I see you trying to respond to this, but I don't hear you. I don't know if this. Um,
You
well,
don't hear me.
oh, now I hear you. I don't anymore.
Now still cannot hear you.
Yeah, it came in and out. I'll say, I know that there's a standard argument for computably branching trees. And so if you kind of basically, and it's not too hard. It's kind of an exercise that I remember doing in graduate school. So I I assume it's essentially the same kind of argument where you take a computably branching tree and then uh, find a tree that's also coded in the model that that would be that would actually be binary, but a branch in one
Oh,
corresponds
I
to.
see.
And so
Okay.
it's yeah, it's kind of an exercise that we is it that I think you can convince yourself.
Yeah.
And
I
once
have
you
a
convince
second
yourself that,
question.
yeah, go ahead.
A second question, and again, excuse me if this is completely dumb. It's also not well formulated. So Harrington has this forcing argument where he shows that WKL0 is conservative in the first order part over RCA0, I believe,
Mhm.
right? So I maybe it's obvious, but I'm just unaware. Is there also a similar conservation result for WKL0 plus, say, B sigma K plus 1 with RCA0 plus B sigma K plus 1?
Yeah, I think so. Yes,
Oh,
you can
okay.
always expand.
So I mean, I couldn't really follow all of the details of your talk, but it seems kind of intuitively that you are using this conservation result because your
Yes,
pivot argument is the WKL0 is able to get this uh, show regularity, and from that you have the boundedness, and then you
yes,
drop
yes,
down with the conservation result, and that is the way it's.
yes.
Is that correct?
If yes, I mean the weakest theory I think is B sigma 1. As long as you have B sigma 1, then you can freely expand to a model of WKL.
Okay. Okay. Thank you.
Leszek, I can't hear you again.
That's now. Can you hear me now?
Yes.
Yes.
That's pretty terrifying. I don't know what's going on, and I'm supposed to give an online lecture tomorrow. So it's not just my voice, it's also the mic, it seems. Anyhow, the thing is, at the level of B sigma 1, it's a very different well, it's again an external forcing argument. Given a tree, you force to add a path through that tree, and you ensure that B sigma 1 in the ground model allows you to preserve B sigma 1 in the forcing extension. At the level of B sigma 2, you're basically already able to take advantage of a formalized low basis theorem.
Yes.
So you can make your path through the tree assume it's a computable tree just for simplicity. Otherwise, you relativize it. So the path through the tree, its jump is delta 2.
Right.
Yes.
Which means if you had delta 2 induction because of sigma 2 collection, you also have delta 2 induction about the path that you added.
Yes. It's
We
a
have
low
sigma
basic
2.
theorem.
Yeah,
Okay.
that's the idea. That's probably the simplest
Thank you. That's
yeah.
very nice.
underlying reason that I can suggest.
Okay.
Good. Other questions?
Just a remark that it's wonderful to be at a talk that ends with KC question has a positive answer.
Uh-huh. You mean it is already answered? Where can I find the answer?
No, I mean it's just a positive thing in this in these troubled times. That's gives one a good feeling.
Yeah.
Okay. Okay.
And it also reflects well on Clote and Kaufmann that their intuitions were good.
Yep.
Well, this is due to influence of the Paris Logic Group that you organized and maintained for a number of years.
Mhm.
Well, thank you.
Okay. Any other questions? Okay, not seeing any. I will just remind everyone. So we'll thank our speaker, but before we do that, let me just remind everyone. Next week, we have Piotr Gruza from I believe Warsaw, and I don't have a title yet, but I expect he'll be speaking about notions of solidity and neatness and tightness that I believe were introduced by Albert Visser and explored by Ali Inayat recently as well. So expect to see the title and abstract on the New York Logic site soon, and we will send out the information. And we will be moving forward, staying at this Zoom link for at least for this semester. Let's thank our speaker again. Thank you very much, Sun Mengzhou.
Also, thank you for the organizing this.
Nice.